I'm Garland Best with OZ Optics Limited. Every year across North America and around the world, storms cause trees, poles, and branches to fall onto hydro lines. More than half of all power outages are caused by fallen trees. Utility companies send emergency crews out after storms to find and clear fallen branches as quickly as possible. Otherwise, power outages will occur, or worse. Naturally, it would be extremely valuable to detect and locate such problems the moment they occur. But how can this be done? Recently, utility companies have installed optical fiber cables along their utility lines. Optical fibers are non-conductive and can be installed in the same cables as the electrical wires without any risk. One can then use the fibers as sensors to detect problems. One approach uses what are known as optical time domain reflectometers, or OTDRs, to monitor fibers. These instruments send optical pulses through a fiber and listens for echoes. If the fiber is bent sharply by a tree or branch, either a strong echo occurs, or echoes farther along the optical fiber get weakened or attenuated. However, it takes quite a strong bend to cause even a small change in these echoes. Here at OZ Optics, we have developed a different instrument called a Brillouin Optical Time Domain Analyzer, or BOTDA. This instrument also sends pulses and detects echoes, but from a special process called Brillouin scattering. The instrument not only measures the power, but also the frequency of the echoes. If a branch falls on the fiber, it will stretch the fiber, and this will change the frequency of the echoes reflected by the fiber, in much the same way as tightening a guitar string changes the frequency that it vibrates. The BOTDA instrument detects this stretching or strain at much weaker levels than are needed to cause a signal change that an OTDR can measure. To demonstrate this, we have set up this experiment. This will simulate a fiber along a hydro line. We've laid an optical fiber here between two posts, emulating where the hydro line may be installed against two hydro poles. In between, we have this movable wedge, which will function as our branch in our test. We can adjust how much the branch presses against the fiber by adjusting this dial, which raises and lowers it. This fiber is connected to a large reel of fiber here and another reel of fiber here, totaling about 16 kilometers worth of fiber, to simulate something approaching what would occur in the real world. We are going to try to detect changes caused by this wedge using the following two instruments. The first instrument is a conventional OTDR system. The second instrument is the OZ Optics DSTS, Distributed Strain and Temperature System, which works based on the BOTDA principle. We will compare the results from both instruments and show you how much more sensitive the BOTDA process is compared to a regular OTDR. Let's start off by measuring strain using the OTDR. Right now, I've left the fiber completely slack. We can move it up and down. There's no tension on it. Okay. Our screen here shows the output from the OTDR. This curve here, gradually going down, it's a signal that is measured by the OTDR unit. It is a fairly smooth, flat, uniform line. what we're going to do is apply tension to the fiber by raising our wedge until we get to the point where we can actually find a spot where this line shows a dip or bend. So to do that, we just start increasing the height on our wedge. So I've tightened this up to a level that I know will start to generate a signal on our OTDR. So we're going to start a scan and see what we get. Okay. While it's scanning, let me tell you a few details about the settings we have used. Okay. We've set the OTDR to send out pulses that are 10 nanoseconds in duration. At this setting, it supposedly has a resolution of about 1 meter, corresponding roughly to the section over which we are stretching the fiber. Okay. We've also set it to average its signals over 60 seconds. It's important to use a long enough averaging time for it to detect the signal amongst the background noise and all the echoes. So for the maximum sensitivity, you have to use the longest time that is practical, okay, without it being so long that it takes forever effectively to get a measurement. It's about 50 seconds up the way through the reading. We have about 6 seconds left. And now it's done the measurement. If you look at the curve, it looks almost exactly the same as what we had before. There's very little change in that curve. But if we zoom in very carefully over the region, you can actually see a small change in the curve, showing it is now detecting that variation. And as you can see, it is quite a small change here. Okay? So these are the signals and changes that you have to pick up with an OTDR in order to detect the strain on the fiber. And as you can see, it's a very small change. And it's hard to pick those changes out compared to the background noise within the OTDR signal. Now for comparison, let's hook up the fiber now to our Brillouin sensor and make the same readings without disturbing the fiber. Alright, so now that we've done the measurement with the OTDR, let's measure the signal using the Brillouin sensing system. I have it already attached. I'll start recording data. Now, just like with the OTDR system, we're using pulses that are 10 nanoseconds in length, which will give us a resolution of about 1 meter through our fiber. We are also doing averaging. We're averaging over about 10,000 samples. Again, we're doing this in order to have an accurate signal with low noise. So the conditions are similar to what's being done inside the OTDR. So this will make a good side-by-side comparison. While we're measuring the data, let's talk about a couple of the differences between the BOTDA and the OTDR. One critical difference is that we actually hook up both ends of our fiber to our BOTDA system. Okay? And we are launching light in the other direction. So light is traveling through both directions of this fiber. The light in the opposite direction is being used to amplify the signals. And this allows us to make measurements over a much longer length of fiber. than what's achievable with this OTDR. We can use our system to measure changes in strain or temperature over distances longer than 150 kilometers. This is obviously important for hydro applications where you're running lines from community to community. Being able to measure strain and temperature and detecting issues over distances of 100 kilometers is obviously very important. So that's one advantage that we have with the BOTDA concept. It's finished taking the data and is right now analyzing the results. We can always monitor the process through this little status bar right here. It's currently about half the way through. If you recall, with the OTDR, we had a very hard to see signal. Let's see what the signal looks like with the BOTDA. So looking right here, across our line, we see a very sharp spike at one location. This is where we're applying the strain. If I zoom in, you can see how clearly we can actually observe that spike in the signal. The peak here corresponds to a strain of 558 microstrain. For comparison, our background signal is around about 7 microstrain. So our signal that we're seeing here is roughly 70 times stronger than our background signal. Okay, so we have a very good signal-to-noise ratio and can easily detect this strain, which was so hard to see using the OTDR system. For our next step, we're going to reduce the strain that's introduced by our wedge, show it again on our system, and see if we can detect anything on the OTDR. Alright, so we've lowered our wedge to reduce the strain on the fiber. We've made a recording of the strain on the fiber. And if you look carefully in the center here, again, we have a peak. It's lower than what it was before, but it's still quite easy to see. It is still well above the background. And if we take a reading off it, it's about 257 microstrain compared to a background level here of around less than 17 microstrain. So again, we have a signal here that's about 15 times as strong as what our background level is. Very easy for it to detect. Let's now disconnect our fiber from our Brillouin sensor and hook it up to our OTDR. Disconnect the other end of the fiber. And let's try taking a measurement. So as you recall, before we had a very small change on the display from the OTDR when our strain level was about 550 microstrain. Now that we've cut it down to half, will we be able to see anything at all? Again, it's taking about 60 seconds to record the results. So we just have to wait until it's done. From a time point of view, obviously, getting measurements within 60 seconds or 120 seconds is actually quite reasonable, given that you need the time still to deploy people out to where the branches or whatever that's landed on the power line has fallen. So getting updates on a minute-by-minute basis is extremely responsive from a hydro application. So it's done the measurements, and we're going to zoom in the area question, which was between 7.1 and 7.3 kilometers on our fiber. And so if we're looking here between 7 and 7.5 kilometers and zoom in, there's basically nothing that we can distinguish from the background signal. Okay? It basically looks like a random variation with no noticeable jump occurring in the signal. So the OTDR is not detecting a strain which was so obviously visible on our Brillouin sensing system. So this clearly shows how the Brillouin sensor is capable of measuring changes of strain on a fiber on orders of magnitude greater than what an OTDR can detect. Okay, roughly speaking here, we have a signal-to-noise ratio of anywhere between 20 to 50 to 1 that it can measure a signal on a BOTDA while being undetectable with an OTDR. So this should clearly show you the advantages of the BOTDA system for detecting issues along hydro lines, allowing you to detect smaller events and be able to react to problems before they become big problems, potentially disasters. Thanks for taking the time for watching our presentation.